Recording started.
All right, guys, I'll just repeat something I said just a moment ago, which is basically that we're going to go over a lot of the concepts that are on the test, or at least concepts that we didn't touch on the last recording. So between these two recordings, you should be able to really get a pretty good handle on a lot of the concepts that are going to be on the test. Also, just wanted to mention that when you look at the recording, the text tends to be smaller unless you change this menu button up here to 100%. So just wanted to mention that as well. So just going over a few things we went over before. Again, when we have columns in the same group, they have similar properties, right? And so groups are known as families, and the rows are known as periods. And probably four of the most important rows to know, or sorry, not rows, columns to know. Group 1 is the alkali metals. Group 2, alkaline earth metals. So it's not quite the same, right? Alkali, alkaline. Group 17, over second last column, is the halogen gases. That's like fluorine, chlorine, bromine, that sort of thing. And then group 18, those mysterious guys, the noble gases or inert gases. I'm not really sure why they're called the noble gases. Maybe it's just because they are, you know, like a king or a queen just kind of is maybe sitting on the throne, not necessarily, I shouldn't say necessarily doing anything with anyone, but anyways, we won't go there anyways. But noble gases basically, you know, they don't react with other gases sort of thing. So as far as the most reactive elements, remember they're in columns 1 and 2 of the table as well as column 17, so the halogens. And remember, oh, hey Ashley, how's it going? Oh, I think Ashley just got kicked out again. Yee. Not good. So again, properties of metals, these ones are fairly, you know, you guys know these, right? Shiny and conduct electricity. Just remember those are physical properties. And some examples of chemical properties. Chemical properties are always how a substance reacts to other substances. So usually we're talking about things like oxygen and water. Those are two of the more common ones. Okay. Hopefully Ashley is able to get back in. So just really briefly, guys, state the names of the three most reactive groups in the periodic table. Can you guys tell me those? Okay, 1, 2, and 17. And again, first group, alkali metals. Sorry, maybe I should let, yeah, like David said, alkaline earth metals, those are the second ones. Alkali metals are the first ones. And halogens are number 17. Okay, part B here. What's the trend within any group or column as far as the reactivity of elements? Can you guys remember that one? More reactive as you go down. Good stuff. Then also just thinking about how ions form. Remember, calcium is in column 2, which means that it has 2 valence electrons. And of course, it wants to lose those valence electrons to get an 8 outer shell. There's kind of a shell that's below this shell, right? And so what we can figure out as far as the charge on it and as far as the number of electrons and protons you'll have when it reacts, if you look on the periodic table and you look on the atomic number, remember that's a smaller number, that tells you both the number of electrons and protons. So since it's 20, it starts with both. Sorry, I'm just going to check my email real quick. Sorry guys, Ashley was just sending me a note. I'll just type her a quick email here. She's having some troubles there, computer problems. So yeah, the fact that we know that this is atomic number 20, we know that it has 20 electrons, 20 protons, and it wants to give up these 2 valence electrons. So if it gives them up, since electrons are negative, it's going to become more positive. And since we can only give up electrons or gain electrons, it's going to give up 2 electrons, and we're going to have 18 electrons, 20 protons. So that right there shows you why it has a charge of +2. And remember that this Ca plus 2 is the most stable form. Okay, so how about when chlorine reacts to form ions, what form do we get? Hey Ashley, are you, can you hear me okay? Okay, I hope you don't get kicked out again. What was the reason you were saying? Okay. All right. So what we're doing actually is we're just talking about when we have charges on a certain ion, we're talking about how you can figure out the number of electrons and protons, just some review stuff for the test. So Mitchell was asking me what form do I mean? Well, what I mean by that is when chlorine reacts to form ions, whatever charge you see in the periodic table is the most stable form of chlorine. In other words, it's not an atom, but it's an ion. It's the most stable form. And so you're saying it wants 1 electron. That's right. And so what charge is it going to get based on the periodic table? Well, actually, remember, if it wants 1 more ion, it's going to be a -1, right? Remember, it's got 7 outer electrons. It's in group number 7. And so it wants 1 more electron. So it's going to be Cl -1. Okay, so how many electrons and how many protons will we have? And I'll tell you first of all that chlorine has 17 as its atomic number. So how many electrons and protons do you think we'll have when we get the Cl -1 ion? That's right, we're going to gain an extra electron, so we're going to have 18 instead of 17, and we'll still have 17 protons. Okay, so when we go on the next page, that's just reviewing what we just talked about. Okay, so you guys remember this electronegativity table? And basically that tells you how much an atom wants the electrons that it has. The more electronegative it is, the more it wants the electrons that it has. As you go this way in the periodic table, it's more electronegative. It's less as you go this way. So remember, we need to know that for the test. So question here then, of the compounds below, which one's going to have the highest boiling point? Now to figure that out, first of all, we look for hydrogen bonds, right? Because those are the strongest bonds. So if any of these guys have hydrogen bonds, that's going to influence the boiling point the most. Because the stronger the hydrogen bonds, the higher the boiling temperature. Because it takes more energy to break those bonds, right? Okay, so the question is, which pair of elements has the greatest difference in En values when we look at the table? And so we're not going to actually do that right now, but just looking at it here, you can see that hydrogen and oxygen have the greatest difference. And so because of that, H2O is going to be the answer. Okay, it's got the strongest hydrogen bonds. So looking at the question here, it says, explain how we calculate the strength of ionic bonds. That's kind of part A, you could say. And part B, how does this strength affect the boiling temperature of a molecule? Can anyone answer part A of that? Okay, bigger the difference in En value, stronger the bond. Good. And how does the strength of the bond affect the boiling temperature? Okay, so we can tell based on its ionic charge. Yeah, you can, but like specifically when you do the calculation, you also do have to use the En table. But it does influence the charge as well. Okay, and the higher the electronegativity, the stronger the bond. The higher the difference, yeah, the stronger the bond. And so the higher the boiling temperature. Okay, good stuff. So, so that's basically this stuff here. And so we got another one here that has to do with boiling temperatures. This one's a little different. So first of all, when we would look at them, again, first we look for hydrogen bonds, right? And hydrogen bonds, remember, they're formed by hydrogen and some element that's in basically the last two columns other than this one here, they have the strongest electronegativity. Now, since none of these guys here fall in those columns, we're not going to get hydrogen bonds. Okay, so since we don't have hydrogen bonds, we look at something else. Now, the something else we look at after hydrogen bonds is which one of these guys has the element that's got the most electrons. And remember, the more electrons, the further we go down in a column is more electrons, and the further we go to the right is more electrons. Okay, so we're going to check these guys out, at C, Si, Ge, and Sn, and see which is the largest of them. Because what happens is, the more electrons you get, those electrons from the one atom repel the electrons from the other atom, and that's what gives you a slightly negative and a slightly positive charge. Okay, so you can, so David's saying it's going to be Sn, and yeah, we can see that Sn is further down than C or Si or Ge, and so it's got the largest atom, and so it's got the most electrons, and so it produces a dipole-dipole situation. One side's negative, one side's positive. Does that make sense, guys? Okay, good, and that's because of all those electrons that are repelling the other electrons, producing a charge. Good stuff. Okay, so question 4a, explain two types of intermolecular forces that affect boiling temperature. Or list them, I guess you could say. Okay, London forces. Electronegativity, and what that produces is the dipole-dipole force, right? Okay. One more? Right, hydrogen bonds, and that's the one that affects it the most. Okay, so again, how does each factor come about? In other words, how does the dipole-dipole interaction come about? This is the one we just looked at. It's influenced by what trait of an atom? What is it about an atom that could produce a dipole-dipole? The amount of electrons. Good. And how do hydrogen bonds come about? Large difference in electronegativity. Good. And usually the last two columns before the noble gases. Okay, good stuff. Right on. Okay, so you guys remember this stuff about VSEPR theory. And remember, what we want to do is we want to look at the electron dot diagram, and we use that to come up with something like this, like AX4. Remember, the A stands for the central atom. X4 means there's 4 outer atoms. And if we happen to have a lone pair of electrons, that would be E. So we could have something like AX3E, for instance, or AX4. Remember, we use that in the chart on page 55, which you can use on your test to find the shape. And so if we knew it was AX4, we could find that this was the shape here. And so I couldn't find the exact chart that we have in the textbook, but this one here shows we're talking tetrahedral because we have AX4, tetrahedral. All right, so know how to do those. And okay, here's something. Remember, it's actually not just hydrogen bonds that affect how much, different things like boiling temperatures. Sometimes you have more than one hydrogen bonds. And when you have that, that affects the amount of hydrogen bonding overall a fair amount. So for instance, if you look at all these guys here and you try to figure out which is going to have the strongest hydrogen bond, if we looked at the difference in En values, I don't have them written out here, but if you looked at them, you would say the difference between H and S is small difference between O and H is large, and the difference between H and F is largest. Okay, so if you looked at just that, you would say that these guys would form the strongest hydrogen bonds. But it turns out that because they're sort of similar, the amount of hydrogen bond or the difference in electronegativity with these two compounds, because this compound can form two hydrogen bonds, it's going to have much stronger hydrogen bonds. So the answer would actually be A. Okay, so because of the fact that it's fairly similar, now you look at the fact that there's two hydrogen bonds per molecule and just one here. Okay? Okay, what I wrote here is that drawing a diagram helps you to see where hydrogen bonds occur. So for instance, if somebody just gave you this molecule here, CH3F, you might not necessarily know, just to look at it, whether the H's are bonded to the C's, or the H's are bonded to the F's, right? But when you draw it out, you can see that the H's are all bonded. I'm having trouble with that. Sorry, guys. The H's are all bonded to the C. So because of that, we know that this doesn't form hydrogen bonds, right, between C and H. It's not a large enough difference. Okay? So because of that, if we're asked anything about this molecule, we know there aren't going to be any hydrogen bonds. So if we were asked which bonds do occur, we know first of all that London forces occur with pretty much any molecule, and we also know that we're going to get some amount of dipole-dipole, because there is a small difference in the values between C and H, and that's enough to make a dipole-dipole. Okay? So also remember, guys, that going from weakest to strongest, the London forces are the weakest, dipole-dipole are the next strongest, and the hydrogen, of course, are the strongest. And just reviewing quickly, well, we know that dipole-dipole is when there's a difference in EN values between two bonded elements. H bonds are a strong dipole-dipole between H and an element with large value. And I just wanted to point out the fact that the H atoms are called unshielded because the other atoms, such as fluorine or oxygen, wants to pull the electrons away, and that's why H atoms are unshielded. Okay. So just list in order from weakest to strongest. You can just use, if you want, you can just use one letter. Okay, so London, then dipole-dipole, and then hydrogen bonds. Good stuff. All right. So I also wanted to point out the fact that sometimes lone pair electrons can affect the shape of a molecule. I don't know if you guys remember, we had one problem in one of the homework assignments where it said, why is it that if you have two molecules and both of them have a central atom and three outer electrons, why is it that with one of them, when you measure the bond angles, they're 120, in other words, 360 divided by 3, but with another one, they turn out to be not 120, but 109.5. Why is that? Well, the reason that is if in the other molecule you have a lone pair of electrons, those electrons, of course, electrons repel, right? They have a negative charge, so they repel other electrons in other atoms. And what that does is it closes up these bond angles. So instead of being 120, there's something like 109.5. Yeah, so then you sometimes get shapes like the bent shape from page 50, yeah, if that was 55 or 59. Okay, so maybe I'll just answer this one because we just went over it. How would the lone pair electrons affect the bonding angles? They would reduce the bonding angles. Okay. All right. So this here is just kind of a reminder that when we have paired electrons and lone paired electrons, it's the lone paired electrons that represent the bonding capacity of an atom because only they can bond with other electrons. It's these lone pair electrons do not represent the bonding capacity. Okay? All right. Now you guys are probably really familiar by this point with the naming system for molecular compounds and ionic. So again, it's only molecular compounds where you say things like di, tri, di here because there's 2 oxygens. Okay, so we won't go into that too much. Just need to know that for the test. Also, I know I mentioned to you guys about knowing both the formulas and chemical names for polyatomic ions. Again, you can pick it off here. The charge, so CO3 minus 2 is carbonate. So if you needed to write up the charge, you would know that CO3 minus 2. Okay, I wanted to mention something else, guys. You guys remember that if you're talking about manganese 4 sulfide, the 4 part of it, you can't recognize that by looking at the formula that you come up with, because the actual simplified formula is going to be MnS2, and there's no 4 there. So again, remember that that 4 comes from the fact that it's Mn plus 4 and not the Mn plus 2, which is the other form of manganese in the periodic table. Okay. The other thing I wanted to mention, if you hear the word systematic name, remember that's just a chemical name. It's just another word for chemical name or chemical formula. Sorry, not chemical formula, chemical name. So this here, for instance, is the systematic name, right? So for instance, if you're talking about water, dihydrogen oxide is the systematic name, whereas just plain water is the common name. Okay, so one thing I wanted to point out, guys, is if you have a compound with a transition metal and there's only 1 ion for it, then we don't use this Roman numeral system. We name it just like it's a molecular compound. So for this one here, scandium trisulfide, we call it discandium trisulfide. Okay? So again, this one here, because there's only 1 possible ion, plus 3, we don't call it something like, manganese 4 sulfide. We name it as if it's a molecular compound. Okay? So that's important to know for the test. And okay, so this is how is the naming of a compound with a transition metal different when there's only 1 possible form of the ion? We just talked about that. All right, so let me see if we're at the end. I think we might be. Sorry, guys. Sometimes I press this button. I think it's because we're at the end. Sometimes I press it and we're not at the end, but this time we are. Good stuff. So, guys, if you do have any other questions about lessons 3 or 4, please send them over. I'd be glad to help you guys. And other than that, please, you guys know the routine. Check out the recording, practice the questions on it, and do great on the test. And again, remember that we have the unit test on Monday, and not the unit test, the quiz is on Monday, and then the unit test is, can anyone remember? Because I can't remember just offhand. I think it might have been, I better not say actually. 13th? Okay. Thanks, Mitch. All right. So thanks a lot for coming, guys. I always appreciate your participation. You guys are great. Yeah, so you bet. My pleasure. So hey, David, I hope your roofing goes well. And here, I'll just stop the recording at this point, guys.